Dr. Chang, I think that you might be muted if you're talking. I can't hear you at least.
Oh, yeah. Okay. I'm sorry about that. So, okay. Again, I before I last time we talked about ended with some Monte Carlo method. Before we go back to that one, I like to give another review, just summarizing what we gone through so far. So for probability, we can have discrete random variable and continuous random variable. For discrete random variable, we have this the distribution function for that variable is known as the probability mass function. And because each of the value of that function is just the probability, so it has to be bigger than equal to 0. And it has to be less than equal to 1. So by convention, if the probability is equal to 1, then it's it always happen. So also because we can sum of all outcomes, it can only occur for one of those outcomes. If we sum over the PMF of all those outcomes, we should get back to 1. And for continuous random variable, we have the PDF instead. And note that again, if we consider PDF, most likely if we say px, of course it will be bigger than equal to 0, but oftentimes it will be equal to 0 because you cannot precisely say that what's the probability for a continuous random variable, let's say from 0 to 1 is exactly equal to 0.5, because it can have 0.550001 is still not 0.5 basically. So instead we can only call the PDF here really saying if we given a range there, let's say 0.5 to 0.51 here, then the probability will be approximately probability of that will be approximately p 0.5 times 0.1, or maybe I take an average for that, or sorry, it should be 0.01. Let me write better, p 0.5 plus p 0.51. I take the average of that. Let's just take the midpoint here, let's say, and times 0.01, let's say. So, or you can think of the area underneath is actually the probability. So therefore, here more precisely, if I have the random variable to lie with a range like A and B, the probability should be just the integral of that PDF from A to B. And so therefore, if also similar to the case for discrete random variable, if we take the integral of Px over the entire range there, entire real space, we'll get back 1. And another thing is important to mention is marginalization. So I hope by this time you're very familiar with this. If I have y here, some random variable y here, I can insert a dummy variable x and then sum over x, then it will get back my original y. Or you may start with here as well. If I want to remove one of the random variable, I can just sum over that random variable and it will disappear. So that's marginalization. And then the conditional probability is defined by Bayes rule, or you can, as I mentioned, this is very lateral. In practice, often you're actually given the conditional probability and you're regenerating the joint probability just using a Bayes rule. And know that this is, I give a remark here. For the conditional probability, if I sum over x here, this is if you think of this, what is px given y? It's almost like you have x and given y as a parameter. It's some kind of parameter. If you have a different y, you have different distribution of x. So it's really a distribution of x. So therefore, if you sum over x, you should get back 1 here. assuming like x is a discrete random variable, just like this case here, right? It just get back to this case here. But know that like you don't have something like that. It is obvious, but like beginner tends to make this kind of mistake. And as I mentioned, I can generalize this base rule into something I call it a chain rule. It's like more convenient. So if I have like x, y, z, I can just like px and py given x and pc given xy and so on. And you can start with any other orders as well. And now independence and conditionally independence, conditional independence. For independence, this is a typically the condition you learn when you first learn probability. But as mentioned, because of the chain rule, you always have this. So therefore, combine these two conditions, just saying that like if you have like x and y independence, you have this one. And it's very natural to interpret this one because like the conditional probability given x, if you think of like py x here, again, is think of like some kind of like py parameterized with some parameter x here, right? So no matter what x I give you, this is still the same as the original py. So therefore, x and y must be independent. And also for conditional independence, this is the condition you will first learn. That given z here, pxy given z can split into this to the product of these two terms here. But again, it seems to me it's better to kind of like think of like using some kind of chain rule again. Like if I, for this one, I just use the base rule or chain rule to expand that. I have this one. So conditional independence just means this. Like if I have like x and y conditionally independent of z, then it's just I have this one given z is equal to this. So you see like given z on both sides here, it doesn't matter. Like if I think of I'm using this distribution to try to predict y, right? Predict y somehow. Because I think of that. Like if I have I ask you like give you some distribution here. Let's say some distribution. This is y here. This is py here. Now just want to ask you like give me an estimate of y. So one good estimate, sometimes people call it a Laplace estimate. We simply pick the p, right? The one that we have highest probability is the estimate, right? I would say like if I give me a good guess of y, then I just take the peak here. So the one with the largest py, let's say this is a y0 here. I would just say, okay, y0 is my good estimate because it has the largest probability. So same thing here. Now here I don't have any additional information given to you, but here I may give you some additional information as a z or x here. Now what it's saying is that if I give you z here, now it doesn't matter if you give me x anymore. Right? So because I give you z here, I give you x is still the same distribution, right? If I consider that this support this p, let's say y given x, let's say for a particular x, py given z, c, for a particular z, you give me this. Now, if I also give you this information x here, I still get the same curve here. So the estimate will be exactly the same as before, right? I really should improve my handwriting. I'm sorry about that. This is z and x. So therefore, like this x and y must be independent when z is available. So therefore, like x and y conditionally independent given z. And again, I want to emphasize again, like these two things, no pun intended, but like they are independent. If one, if you have something is conditionally independent, conditional independence, it does not imply independence, and the other way around as well. Like it doesn't imply the opposite. Okay, so here a very quick summary of this thing, and I want to mention this because I'm just thinking like I probably should use the okay, maybe before that I just want to give you a kind of a small quiz of like this information here I just given, so you should be familiar with this, but okay, maybe I will switch to my tab. Just wait a sec. Try to connect from here. Okay, I need to grant myself a co-host permission. I guess I need to unshare here as well. So let me move my mic a bit closer. Okay, hopefully this will work. So okay, like I guess we went through this a couple of times, but I guess it's good to use the same example. So from the for the Monte Hall problem, I hope you still remember that. Like we have like 3 doors and so on. And I want to go through the proof again, but just want to quiz you, like if you're really following me. So now let's say like we always switch. So remember, okay, maybe quick recall like what we have in that problem. So a guess is going to pick a door. So at the beginning, like let's say maybe pick the first door. Maybe I will denote this as a G1, like pick the first door. And then like there's a price in one of the behind one of the door. Maybe there's a price here. There's P here. Maybe I can denote this case as a P2 here. And then like the host will open the door that does not have the price, and also like was not chosen by the guest. So therefore like the host will open this door. So once it opens this door, it will ask the guest whether he want to switch his decision to the other door. So if he switch, then if we switch, then in this case we switch to this door. Right? So because this door is not open, he will pick this door. Otherwise, he's going to stay. And we mentioned that okay, the probability of like staying is like of apparently is just 1/3. Now for probability that it considered to switch, the probability of winning. So this case, I'm assuming that like we are going to switch will be equal to probability of winning. So let's say I can have like case price at door 1, price at door 2, plus price at door 3. So okay, what's the reason I can write this? Simple question here. Why I can do that? So what was we just review the materials at the moment, right? So that what's the name for me to do? Uh, exclusive. Yes. Oh, okay. The question is like what when I write this is equal to this one, like the left hand side is equal to right hand side. What's the reason that I can write like this? I'm starting with an M. Yes. This is just the marginalization conditions, right? So just want to make sure you guys. Yeah. You can repeat the answer. Just let me know that you are here. So this is a couple of simple questions, but I want to make sure because this is important. I will further elaborate why I think this is important after this. So now then, let's see, I can write this as probability of win. Yeah, it's okay. Yeah. Yeah. Okay. So I can write this like expand as like P1 plus probability win P2 plus probability win P3 P3. Let's say I write like this. So again, why I can do that, or like what's the reason that for me to allow me to write like this? Yes. Yeah, base rule, or you can even call it chain rule or something like that. Yeah, this is just base rule way, or like yeah. So and then and then I can write like this, right? This is 1/3, 1/3 as wind PV 1/3. So I'm not going to ask you why I can do it like this, but you realize that I can do like this because I am assuming that the price is randomly chosen or like uniformly chosen among the three doors. Like this is like the setup of the problems. Of course, I can have like different prior condition. Maybe like I have a tendency to choose to be more likely to choose the first door than the second door. Then this probability won't be the same. But in this case, I'm assuming like we are assuming that like all of them are equal likely to be chosen. And then like then this is like you afterward. This is just okay. If I as okay, I didn't really okay, at the beginning I forgot the condition here. Besides we are going to switch, we are assuming that like the gas is going to pick the first door. Gas pick first door, door one. Or like G1, that's the condition that we assume like this. Then the gas picks the first door, then the other door picked by the gas will be like this one, right? So the second door. So therefore, like uh, if the price at this one here, oh, okay, sorry about that. Actually, I this depend on the case. So if gas, okay, let me repeat. I got confused myself. So again, I forgot to mention, in this case, I assuming the guest always pick the first door here. So if the guest pick the first door, if the price is the a door one, of course, like then if we pick the other door, like you will always lose, right? So there will zero here. And if like the price is in the second door, or maybe like just in this case, if the price is the third door here, then the other door, of course, will contain the price there. and when we switch to the other door, we'll always win. So this will be 1. And the same case here, it will be 1. So therefore, like this 2/3 will be the overall probability. So here, I'm just repeating like what we discussed so far. So, but now I want to kind of like just to before I go into the Monte Carlo method, I want to emphasize like this. I call it a engineering approach. Let me share my screen again like, on my computer. Here I'm promoting an engineering approach, or like I could even call it a dummy approach to solve like any probability problems. So you see like I would again I take the multi-hop problem as an example. So you have a kind of like a probability problem that you are trying to solve. Like first thing, okay, I've listed several steps. Let me move to here. Yeah, and first thing maybe I can introduce some dummy variables. You see like why I'm saying so. Like to introduce some helper variables. In my case, I for the multi-hop problem, I like to introduce a other variable that will the other variable. I mean the other door that both the guest and the host did not choose, or the you will see like what I mean later on. I can introduce this other variable. It will help me a little bit solving the problem. Then I want to identify like distributions and conditions. Like I want to know like what distribution I know, what conditions I know, like any independence condition, conditional independence, and how the variables are related to one another. So then I essentially this is the main step, I guess, or like I want this is like the preparation, I would say. So this one, like what's the probability I try to find to actually solve the problem? For example, in my case, maybe I try to find the winning probability that I always switch, which probability actually contribute to that precise value. I will elaborate again like with my Monty Hall example. So then I can insert some dummy variable. Like basically, I'm trying to solve this conditional probability. I I I may not know that probability right away, but I can insert some dummy variables and then do marginalization. You will see why I want to do that. Then it will allow me to split this variable into pieces that I know the value, or I know the value from the problem setup. So then after that, like I will simply like expand all the conditional probabilities or all the values, and then evaluate them, and then compute the sum integral. So okay. At this moment, you may be a little bit confused, or maybe quite a bit confused. I'm sorry about that. But I guess once I go into that Montreal example, it become much more clear. Like so, if I go back to this example again, so if I would say like use my proposed like dummy approach to solve like this probability problem, then okay, I will first I think of like okay, what are the random variable? Like as I mentioned, I will use shorthand notation. I say like P1 is like the price at door one, and G2 is like the guest pick the second door, let's say. H3 is like the host pick the open the third door, let's say. Now I was first I introduce some helper variables if necessary. So I will introduce a helper variables. I call it O. It's like the other door. This other door is like both the guest and host did not pick. Or let's see. This may not be a good definition. Let's see. Oh yeah, that's okay because that's the exactly the other door because the situation is always I have 3 door here, the guest open one door, and the host open another door. That's another door here. I call it O here. Given guest and host, you have the O is actually deterministic. But let's say I would denote O as the other door just for bookkeeping, right, for convenience. So, and then like now I will try to identify all the distribution and conditions. So these distribution conditions will include, for example, like PMG are independent, right? Where's the price, and where the guest pick the door should be independent. The guest have no information at the beginning, has no idea which one to pick. So therefore PMG should be independent. And oh, okay, I have a precise definition of O, right? O is basically the other door that guest and host did not pick. So I use this a little bit fancy notation here, uh, set what's that called, like set difference. So basically like let's say I have door like 1 2 3. So uh besides the guest door and host door, the other door will be like the remaining one, right? So and also I have the distribution PG and PH will be just 1/3 here. I assuming, oh wait, this PH is probably is incorrect. I shouldn't put PH is 1/3. I'm sorry about that. Yeah, I'll omit this. Yeah, just PG is 1/3, right? So it's like for the gas, it's like uniformly picking order. Actually, I didn't mean PH. Yeah, this should be PP. Yeah, I have a typo here. The price are uniformly chosen at the beginning. Yeah. So next, oh, I need to. Yeah, I need to change this for every slide. So next, identify which probability that actually solve the problem. So now, let's say I have an O here. Let's say if I have the question, what is the probability of winning given switch? Use the switch strategy, always switch. So what's that probability? I mean, just what is the probability? This is a question again. Like, what's the probability? Using the variables here, like P, G, H, O. So what's the probability that or think of like what's the event that that actually correspond to winning given switching, given that like the guests always use the switch strategy. Uh uh what I mean like using the variables I have here, like O, P, G, H, let's say. O, P, G, H here. What is the condition for it? No. Did you are going too fast. That's the final final answer. What I'm asking is like I'm kind of like trying to tackle this problem again using my proposed like dummy approach. Right? Uh, you can say so, or like you can just say like what given these variables like uh when do I will have winning condition? Like is that G equal to H or like what? I mean like that you what's the condition that like I will have the gas going to win the yes, right? So if I define this other door, that's why I like to define this over here. You see like the case of winning in this case is just if I switch to this other doorway, so therefore like the probability of winning given switching is just equal to probability of O equal to the price, right? So I mean, like at this stage, like so that's why I need to this like start with here to introduce some helper variable. So it just gives me easy for the notation here. You don't have the P1 here. Okay, the P1 here is a shorthand for me here. So P1, what I mean by P1 is actually really P1 is equal, what I mean P1 is like the case when P is equal to 1, something like that. So PP1 is equal to probability P equal to 1, something like that. So it's a shorthand notation here. So here, I'm even not assuming. Earlier, I assumed the guess always pick the first door, right? Here, I'm more general. I try to be more general. I don't care. I don't care like what the guess pick. I just start to be completely general. So I don't assume anything here. Of course, I know like without loss of generality, I can kind of restrict to say the guess pick the first door. But let's say if you have more complicated like probability problem and you don't try to find any symmetry like starting from the beginning. So this like is illustrating like how you can do that like without any assumption at the beginning. So I don't assume that like guess pick any door. I just introduce a variable say O here is like the other door that guess and host didn't pick. So if I switch, then basically the guess will pick this door. Right? Now, then therefore like for me to win, the probability of winning will be just PO equal to P here. But now given this here, right, then I'm exactly my problem of trying to solve the multiple problem or like the finding the winning probability when I switch is just trying to find this probability O given P, right? Sorry, not O given P, probability O equal to P. Now, now my O, let's see, O equal to P. Here, I just elaborate a bit more like O equal to P. I can expand this, right? Actually, this is just using let's see. I'm just doing marginalization, right? Let me see. Yeah, I'm just doing marginalization here. So for this one here, I don't know how to find O equal to P here. Let's further like elaborate this. So let's do a marginalization. I have like probability O equal to P given P1. I have several different conditions, right? Sorry, like several different cases, right? I can have like P1, P2, and P3. That basically I can have like the price at door 1, price at door 2, and price at door 3, right? So this probability therefore is equal to this one PP1 plus probability O equal to P, P2, PP2 plus probability O equal to P, P3, PP3, right? So you guys are all happy with this? Oh, okay. By the way, like, do you guys all okay with this? Like, the probability of winning is equal to this. You have any concern or question for this one? Okay. Now then okay. Then here I'm just doing okay marginalization, right? That's the same step we did earlier, right? So or I'm sorry, this may be like for you is a step like a jump a bit more. Actually, what I mean is like this one, right? O equal to P and PI. I can do this way. Yes. This is like just equal to probability O equal to P. You think of this as just random variable, right? This is like some kind of random variable. You can call this Z here, right? Because like O is a random variable, P is a random variable, if you think of like O equal to P is like is something like equal to 1 when this condition satisfied equal to 0 when it's not satisfied, then it would be like some other variable, right? So then I can have like PZ, I can have like another variable say insert to that and then sum away that like using marginalization. So this is like precisely what I did here. So given this, then I can expand with base rule, right? So then I basically here this step I use marginalization first. So this one here I use marginalization first. Here I use marginalization. Then I use base rule here, right? Then for each term I apply base rule. Then I got this. And then know that like what's P O equal to P given P1, right? So if I need O equal to P given P1, that means like I need O is equal to O1, right? Or like I is or something like O is equal to 1, right? Something like that. Therefore I will just shorthand this as O1 here, and shorthand this as O2 here, and this is O3 here. So basically we get this. And now know that like I have all this uniform PP3 is like 1/3, right? So I can put 1/3 out. Let's see. POI. Yeah, here actually I still use the symmetry. I thought I didn't. I still like here. Of course, I for each of OIP I can or you can omit that. So let's say you try to solve like each of these. Okay, let me omit this. Let me omit this. So then this probability switch is just equal to this, right? Now I supposed to find, I know PPI will be all equal to 1/3, right? PPI is all equal to 1/3 here. Now I supposed to find POI, PI for I equal to 1, 2, and 3, right? So let's start with like the 1 here, like PO1, given P1 here. Now I can repeat like the same trick here. I do marginalization. I insert like G and H here and sum over that. So note that like I need this G and H because I don't know the directly how O are related to P. I know like how O is related to G and H, and then G is how G and H, how H will be related to B and so on. So therefore, I need to insert these dummy variables here. And this is like again like the tricks that when you solve a probability problem, like in this dummy approach, you always use. It's like in the problem, again, like let me repeat. In the problem, like after I introduce this O, and I have this P, I know that I need to solve this. But I don't know how O is directly related to P. Like at least I don't see it right away. Like you think of like me as a very, very dumb me. My brain is like super dumb. Like I don't know how O is related to P somehow. So, but I know how O is related to G and H because I always like simply the other door, right? The other door that the guest and host didn't pick. So if I given G and H, I know how O will be related. So therefore, like I try to introduce this variables G and H into the formula there. So then if I introduce that, I can sum it out again. So I put G, H, G, I, H, J here. I need to sum them out. So, and then I try to expand that. So this will be a little bit long. So if I expand that, but know that like this is nothing really special here. So for here, again, I'm just using base rule, right? So I put like GIP1 first, and then given GI and P1, how H is related to G and P, PMG, right? And then given G, H, and P, how O is related to that guy here. So then I would just write out all the summation here, right? So I have I and J sum over like 1, 2, and 3, right? So therefore, there will be 9 terms in general. I just write all of them. Now, if I try to observe each of them, so let's see. First of all, like PG will be all the same, right? Here, I write, okay, let's see. I wrote 9 terms here, but I already grouped some of the terms. Let's see. Yeah. So for G1, the first one, right? PG for I equal to 1 here. This is the first row here is I equal to 1 here. I equal to 1. And then the 3 terms that I sum over J to be 1, 2, and 3, right? So the first one, I equal to 1, right? I equal to 1 and J is equal to 1. This is J equal to 1. So therefore, like this column, like J equal to 1, this is column, this is J equal to 2, and J equal to 3 here. And I have like PGI given P1, this I can pull out of the summation for J, because like this, let's see, this sum can write the sum of Pi and sum of a Pj, right? And this term does not depend on this sum over J. Then I pull out to here. So you see I pull to about, in front of the bracket here. And PGI given P1, because G and P are independent. Now I use this condition here, G and P are independent. I just write PG1, PG2, and PG3 here. And I know this is 1/3, like all of them are 1/3, that's okay. I don't care. So now let's try to make sure like if you you are following me. Let me just randomly pick one of the terms, see if you know what are the values here. Okay, for example, like what was the term here? What's the term here for this one? What's the value for this one? Okay, maybe it's like just see this one here. The first term, like this P H1 given G1 P1 P01, yeah, given G1 H1 P1. Yes, yes. Yeah, it's yes. Great. So actually let's see. This entire column should be 0. It's not just this term here. This entire column should be 0, because when the player picks the first door, the host cannot pick the first door, right? Yes. So look at this term here, the probability here. So I elaborate all the terms here. But if you look at that, like not all events can happen in this problem setting here. So if like basically remember the game here, like the the gas. Wait, maybe I was wrong. I'm sorry. Like I probably should say this entire row is a 0. Let's see. Yeah, this entire row should be 0. Is that? Oh no. I'm right. I'm right. No. I'm wrong. I'm sorry. I got confused myself. Yeah, here the entire row is 0 because if the guest picked the first door. Wait, did I have some typo here? Let's see. 1, 2, 3 here. And pair 1. This is 1, 2, 1. 1, 2, 3. 1, 2, 3. Guess. Oh yeah. I think I wait. I think I shouldn't jump into this conclusion too quickly. Maybe I just look at this term only. So this term is 0 because if the guest pick the first door, then the host cannot pick the first door. Right? So therefore, this one must be gone. I'm actually okay. Yeah, I'm actually so as like for this one also. Right? The guest pick the first door, the host cannot pick the second door. Sorry, the guest pick the second door, the host cannot pick the second door. Let me write better. Right? And then this one also gone. Like guest pick the third door, the host cannot pick the third door. Uh, okay, but yes, but here like indeed like this one, the whole column should be equal to 0 though, but not because of the first term here, but because of the second term here, this will be all 0 because if no, remember that what is the other door is like the door that like the guest and the host didn't pick. So therefore, like if the host picked the first door, like the other door cannot be cannot be the first door. So therefore, all this will be 0 as well. And similarly, let's see, the guest, and this will be 0 as well because if guest pick the first door, like the other door cannot be 1. Also, like here, the same case, like the guest pick the first door, other door cannot be 1. So here, remaining non-zero terms will only be like this one and this one. So if I look at that, yeah, I just write it out like these two terms here. I think it's like this term, you just mentioned is like this term here, and this term here, these two term here. So if I write it out here, so it will be, then finally I just compute the sum, right? And for this one here, again, the G2 is just 1/3, like PG2 and PG3 is just 1/3 as mentioned. And this is just 1 and 1 because if the guest pick the second door and the price at the first door, the host have no choice but pick the third door, pick the last door. I'm also here, like if the guest pick the second door, the host pick the third door, then the other door has to be the first door. Therefore, like this would be just probably the 1 and 1. And same case for these two other cases as well. So therefore, I finally got 2/3. Okay, so I hope like I kind of convince you that like if you came across a probability problem that you don't know how to work on, this probably like an engineering or dummy approach that you may try is just think of like okay, introduce some random helper variables and think of like exactly which probabilities you are trying to compute, and then like try to using marginalization to introduce dummy variables so that you can expand them into a conditional probability that you know how to find based on the problem setup. So know that like I write down all this like expansion here because I know exactly what are this here. This will be either 1 or 0, but I know precisely what are this value. I'm saying same as like for this guys here as well. So yes. And so I just want to give some final remark here. Is that this approach that I'm proposing here is that you can virtually solve any problem, but it leads you like some kind of experience, as you know here. Like you need to figure out, like, for example, what kind of like dummy variable you should insert. Maybe here, right? I don't know. Or yeah, I would say not a lot, but it needs you to have like certain kind of experience sometimes. Uh, and for this approach, but still, I think it's a systematic approach I would recommend. And it it for discrete random variable, basically it can solve any discrete random variable problem. But if you have too many variables, then apparently, like you even if a calculator, after a while, it's not quite feasible. If you try to expand everything here, you just say, um, it's like very painful to do the bookkeeping. So that's why like we eventually we need to some kind of like probabilistic programming, rely on programming to solve the problem. Another kind of like issue that you may have is like if your random variable is not all discrete, some of them are continuous, then the last step here, like some in this case, like let's see, when you compute, like for example, do the marginalization, it means that like this may not be just sum, it can have some integral here. And in some cases, like this integral is solvable. In most other cases, actually are intractable. So in that case, also lead to some probabilistic programming approach. Uh, and actually, in that case, you will rely on like something like Markov chain Monte Carlo. Okay, let's see. So yeah, here I just want to uh, use the let's see Monte Hall problem as example again. So for the Monte Carlo approach, uh, I think of like uh, the the approach we just have here. So we we are able to find the exact solution. It's actually quite systematic, but you still need to a bit of experience, like what dummy variable you're trying to introduce. I would say like okay, yeah, no, you still need that. For this one, you need to find like what kind of variable you need to find. I guess even for Monte Carlo, you need to do that. But introducing helper variables depend on like what kind of program like you're using. uh, some probabilistic programming languages, like probably you don't even need to know that. But if I'm going to show you how I'm going to do that, like later on, like I'm doing from scratch, then I need to have some understanding as well. But in some cases, if you use packages, you may not even need that. So it simplifies even further. So I therefore like if I'm going to do a Monte Carlo, it's even a dummy approach. So um now for the Monte Carlo I just mentioned is that I'm going to solve the problem simply by simulation. So again, if I use the Monty Hall problem as example, what I'm going to do is I just simulate the game many, many times. So let's say I am the I have this game that play many times. Like each time I guess like pick a different door and the host pick a different or the prize put in behind different doors and the host kind of like add accordingly. Let's say I repeat like 10,000 times. I can stick to one of the strategy as a player, as the guest. So I may switch or maybe always stay put. Then I simply count my number of winning, right? So after that, like I can estimate the winning probability just as the number of wins over the total number of experiments. So of course, I doing this, it won't be exact, but uh, I can improve the estimate like as much as I want, as long as I'm willing to pay for the computational cost. So if I'm willing to do more simulations, I will get improved in my estimate. And you see that like the problem is already solved as long as I'm able to even just simulate one case, right? So if I know how to do like one case, how to simulate that, I solve the problem essentially. Uh, and of course, when I say I solve it, in the sense that if we don't need the exact probability, and in many situations we don't actually need the exact probability, so therefore, like this kind of approach is fine. Uh, and but know that like even with simulation, like this can be hard for a really large problem, and computation can be an issue, and can be hard. Is like for one thing we just mentioned earlier, is like if some continuous random variable is involved, then like we may not know how to sample and so on. Like, and then will kind of like lead to something known as like Markov tree Monte Carlo. And I will delay it to much later in this course. After we talk more about information and so on, but we will come back to this later on. So here I just want to give a kind of like motivation, like why we want to do probabilistic programming and a brief overview of Monte Carlo approach. So next thing I want to do is wait a sec. It just give a maybe before the break, just illustrate how we solve that, or how I may solve that, like for the multi-hop problem with a probabilistic programming approach. Okay, let me pull back your chat. By the way, before I continue, like just let me know if you have any question and so on. So and here I assume that like you guys have like some experience in programming. I'm using Python here, and I assume that you know some Python as well. If you don't, like, it's very easy to learn. Uh, and in the course website, I put in some link. I guess in the first class, I guess I mentioned that like you can browse through that if you are totally new to Python. So okay, let's see. Let me try to uh, let me turn off my input method first. How do I? So let me just define a function to simulate one's time. And let me call like simulate once. So start from here. I'm going to use NumPy for this guy here. So I'm not going to use any probabilistic programming packages besides like just the most basic Python numerical packages like the NumPy. So let's see, let me just import NumPy SMP. And let me just simulate one time. Then I will uh, have like the variables I used as previously. I will have like P is the price location, and G is the gas pick, and then H is the host, I say. Host open, which door. Um, and here I instead of like door 1, 2, 3, because Python is like C is the language I by conventions have the index like start with 0, so I would just assume like the doors are 0, 1, 2 here. So let's say then P I will need to like randomly sample like out of like 0, 1, and 2, right? So I would just use a random one in command. So this will just randomly sample like uniformly from 0, 1, and 2. So this is like the door that actually have the price. And then I will have the guess. A guess pick will be another random number again. So for the host, um, I'm basically the host will be, uh, let's say it's going to pick the door, not does not have the price and uh, does not have does not have the price and also not the door that get the gas pick, right? So the host is more or less a it's a 012 minus a p and the gas, right? Something like that. But note that like my p and the gas can be the same thing. So like this is approximately equal to this thing, right? So if I have like p is equal to gas, then I will have like two different values here. So I need to do something more. But let's start from there. So I will do a set difference. I use a set difference command here, set diff 1d. I will just create a 012 here. Here's the MP array. I just convert that into a numpy array so that I can use this set difference. So I have set difference of this one. I'm also like PMG. So PMG, let's say. Now, if I have P is equal to G, then H have two values, right? Then I will just say sample either one of them. So if I H have two values, I use this H dot shape is like okay, maybe I just give some example here like along the way, then show you. Oh, I forgot how to what's the command to insert more oh yeah, below here. So what I mean is that if I have let me just give an example in case you're not familiar. So let's say this is a numpy array. The shape command will give the dimension of the array there. So it's like the size function in MATLAB. So if the shape, so therefore like I have shape 0 here will give how many elements I have, assuming like H is a vector here. So if like it has two elements there, I'll just randomly pick one of them. So H, and then I'll pick an index like of, again, like another one in here. So 2, let's say. This is will be my H. So L, say I will just take H as the first element. And then it will be like my simulation once. So now if I just simulate once here, some values, right? So basically the first one is like, where's the price? And then 1G, the second one is like, where's the gas, which door the gas pick? And then the last one is which door the host open. So I can repeat again, I should get different values and so on. Now then I can do the actual simulation here. Let's say I just define an array like result to store all the results here. And let's say I do 10,000 experiment, like n equal to 10,000. Then for I in range n, this will like repeat this thing like for 10,000 times. So I will just simulate to get PG and H. Simulate one time. And then I also want to define O here as is the other door. Right? So O will be basically other door. So it's like precisely will be like 012 minus H and G. So this one like H and G will be always different. Then always different. So the other door is like unlike this H here, like I mean the set difference. This will only got one value, so I'm good. So let's see. Let me after simulate once. Let me define this O here. as set different again. And O is equal to O0. I know that I need to do that because after this command, I got this array of single element. So I need to pull out the first element here. Then let me append the result. I have PGHO here. So, and then let's make the entire thing as a NumPy array. And I want to do a transpose for that. Okay, maybe I will skip the transpose. So this after doing is like 10,000 times simulation. So I have the result is like this, right? So each row here is basically one simulation outcome. So I like to do a transpose because I want to have each row is basically either like or all the I mean the list of the prices for all the experiment, and the second row will be like the list of the guest picks and so on. Okay, you see what I mean. So if I do a transpose here, I will have like this. Now then I will have a RE rest result 0 will be like just all the price location, right? So then I can evaluate the probability. Let's say I compute the estimated probability. Let's say I'll just pin out the result here. Probability of winning not switch. If I does not switch, it will be just a probability that P is equal to G, right? So the probability that maybe I use a small p here. Probability that like the price is same as like the gas pick. So percent F here, percent. I will have NumPy sum. So result first after the transpose, like the first row there is all the price location, right? So if the all the price location is equal to the first, equal to the gas pick, is equal to the second row here, or like RES1 here. This is basically all the values here, right? So let's run that. This is will be like have 3,000 of that, but I haven't normalized yet. I should normalize it over by n, right? So let's give another bracket here. So this will be approximate probability, right? This is 1/3 as we expected. And then I can do similarly. Probability that switch, then in this case will be like I have P equal to O, right? So it's like the third column, or not third, the fourth column there, a fourth row there. So will be equal to, this is again very close to 2/3. So this like you see like of course what I want to say you can go for like more some other probabilistic programming language are maybe more dedicated to do probabilistic programming, but you see that like even like you use like simply Python and NumPy, you can go pretty far, and as long as you know what you are doing, uh, and and this is nice because you it's you see I didn't really like when I do this simulation here, I didn't try to understand too much the problem. I only the thing I went through is like, okay, I introduce this other door. I know that like what is the actual probability I'm trying to figure out. Um, But once I find that, like, okay, I just based on like um my understanding, okay, the other door has to be the other door, right? So I know how to compute other door, right? So it'd be like just this one. And then the host would be simply uh, the one that guest doesn't pick and also like doesn't have the price. Only when like, and if the guest and price like overlaps, then I need to do something more. And most ways it's very easy to deal with. So and compared with like what we did like earlier, this is much simpler. Of course, the catch is like I won't get the exact probability value, but I can go as far as I want. And of course, like this offer a little bit less insight, right? But at the other hand, like this is very difficult to make mistake. Once you basically you did that, like what I mean is like of course you can have like bug like in your program, but it's harder to make mistake like because of logic. Like when you think through the problem, you kind of like don't get didn't sort everything out. So I guess I guess it's a bit early, but I probably will pause here. Uh, so I'll come back to show another example. Oh, by the way, like I posted an homework. And I believe like uh most of you have. I don't know whether like I miss any of you like introducing yourself in Discord. If you still haven't do that, like please do it today. Like we have this kind of deadline. I guess like this one I don't mind too much, but in general, like the homework assignment, we have the due day is we honor the due day, and like there would be like a slight penalty like for late assignment, late submission. So it's like 5% per day. But this one I probably won't give you any penalty. But if you didn't still like introduce yourself, please do so in Discord. And for homework one is it will be due like next week, and I hope you see that already. It's like just a probability problem, and also like ask you like as an extra credit like to try to solve that using like a Monte Carlo approach, like what I just did here. So okay, I guess I will pause like and come back like in like around 3:30 again. So I'll talk to you then. Yeah. Okay, I guess we'll just continue. What I'm going to do is I just want to do a quick um, kind of quick example, another example of like doing Monte Carlo slash probabilistic programming. For an example we considered like earlier, I guess in last lecture or like the lecture before that I forgot. So I guess it's last lecture. So we have basically like trying to flip a coin. Right, first I guess it's XYZ or something like that. We have a value of a coin, maybe W. I forgot like how we set up the variables. Okay, I want to make sure. Let's me. Yeah, I think it start with W. So we start with W, like have a coin that is like start with like maybe it's originally hat. Like this is a hat here, or like I actually have a hat here. And then like we are going to throw a dice, right? And then like if I don't throw a dice, if I got a 6, then I'm going to flip the coin. And maybe like this is equal to 6, then I flip this coin to tail. I don't know what does tail mean, or like this, oh, oh, or maybe some digit here. So, and then I throw the coin again, this is X. Then, sorry, I throw a dice again. If I got a 6, then I'm going to, maybe this time I got a 5 here. I'm not going to flip the coin, but if I got a um, value like for the dice is outcome is 6 again, then I'm going to flip the coin. I have the coin outcome here. I call it like y here. I'm going to do it again. Right? One last time. Maybe I call this. Maybe I got a 6 again, then I flip the coin again. Then I got a z, something like that. So let's try to simulate this. So we start with hat. The W is just a hat. Maybe I just write like this. W is a hat. So I would just use hat and tail, H for hat and T for tail. And then let's just assume that I start with a hat. Like it doesn't actually matter. Like I just want to carve like use this as a simulation example. Like, but let's for this case I start like I assume that it's always start as a hat. And then like let me define a helper function that like to flip the coin, like if I have the value like x is the coin, like if I'm going to flip this, then I will return hat. If it's originally it's tail, otherwise I return tail. So so this is some kind of like Python syntax is quite convenient. So it's basically it's something like if x is tail, then I will return head. Otherwise, I will return tail. Something like this. So maybe I can test it out first. I flip like head, I got tail. If I flip tail, I should get a head. And then like again, let me import like numpy again. And I will define same thing like a function. I call it simulate once, just simulate the whole experiment one time. So initially, like as Richard just asked, let me just assume like W is hat. So always when I start with the simulation, I assume W is hat. Then what I'm going to do is I will first assume like X is equal to W. Then if the dice outcome, or maybe I can put it together, but okay, let me maybe not doing that. Like maybe I fit the converse, say numpy random. I will use the run in command again. So if this is equal to 5, yeah, by the way, like this is actually basically generate a random number, say from 0 to 5, right? So in this case, or maybe I can even like this, maybe it's equal to 6. So I guess that's okay. Maybe that would be less confusing. So this will be generating a random number from 1 to 6. So if like this is going to be 6, then I'm going to flip the coin here, right? Actually, I need to first initialize that. Yeah. I see. Yeah, that's okay. I will going to flip W, right? Else, then I will just X is equal to W, let's say. So I can repeat this, but maybe I just do it one time. Okay. We return, maybe return X, let's say. Just make sure. So I should be getting hat most of the time, but I have a 1/6 of probability I should get a tail. I still haven't got a tail yet. Okay, something may be wrong actually. Oh, now okay, I got a tail. I feel comfortable for that. So this is I just follow dice once, right? So let's say if I for a couple more times, and like this is a dice outcome like from 1 to 6, and the value is equal to 6, then I'm going to flip the outcome of X. Am I call it Y? Otherwise, I'm just going to say Y is equal to X. And I can repeat that again. like this is like dice outcome is 6, then I'm going to flip y. Otherwise, like c is equal to y. Then let's say I return x, y, and c as outcome. So then like this, like each time okay, it's all hat here. I sometimes got this tail here. This is all hat again. So now let me just simulate that many times. I say I take, again, like n equal to 10,000, just simulate 10,000 times. And I use result again like to store my result. For I in range n, I'm going to append the simulation result. So it gives me a bunch of value here. Result is like head, tail, tail, head, like this kind of stuff. To get it more easy to manipulate, let's see, I can change this and numpy array. And then I can just say like if it's heads, then I will set it to 1, otherwise I set it to 0. So I should have like something like 0 and 1 or true or false like value instead. Let me transpose this again. Transpose that. Then X should be like the first this year. So oops. Yeah. And Y is the second. It picked like no 6 here actually is referring to like actually yeah, I guess you can see help here. I hope that is help. A typo here. So let's see if an example here. So this is basically if I don't give the second element, if I give a second element, it would be the size of the return random numbers. So the first one is just saying like what's the range that you are trying to have the random number. So if I have went in 2 here, it will only outcome like 0 and 1 values. And I have 5 here, it will outcome like 0, 1, 2, 3, 4. Like so I here above I pick 6, so therefore the outcome here will be 0 to 5, like 0, 1, 2, 3, 4, 5. But if you think of it as an outcome from a dice, then maybe I should add 1. It will be easier to understand, I guess. So therefore, like this thing will outcome like a random number from 1 to 6. Yeah. So back to here. Yeah, I was here. I just defined this 0, 1, 2, 3, 4. You see like sorry, 0, 1, 2, 3. Also no 0, 1, 2, 3. 0 result 0, result 1, 0, result 2. That gives me just a list of basically what's the outcome for X. So true meaning that like I got a head, and false I got a tail. So I can sum over that. Let's see how many head I got. For example, like MP sum X, I have a 8, 3, 46. So this should be about 1/6, right? So if like this over 10,000 here, so 0 0.8346, I assume should be close to 1/6, right? Oops, 5/6, what I mean. Yeah, so it makes sense, right? And I can ask like other questions, for example, like what's the probability that like for example, what's the probability X is hat given C is hat, let's say, right? This kind of thing. So of course, you can like solve this like as a probabilistic problem, like, but uh, actually, why don't you try to like do it like numerically? Do you know, not numerically? Try to solve this like for um, I don't know, maybe this is a little bit more difficult. Maybe just this one. What's the probability that x is hat, like given y equal to hat? Maybe like just an again like another exercise for probability. Um, uh, I yeah, I guess I'll give you a minute or two like, to try to. Oh, okay. The question is like we have this previous setup, like we have like the setup we had earlier, have a coin that start with a hat, then we fold the dice, like um if we got a outcome is 6, then we are going to flip the coin. So then we fold the coin again, fold the dice again. If I got a 6, I flip the coin again. And the first outcome I call it X, and the second outcome I Y. Then I repeat, and then if I fold the dice got a 6, I flip it again. Otherwise, I will stay put. And I call the last variable Z. So my question just now is like, what's the probability of X is hat, given that Y is hat? Let's see, where's my pen? Yeah. Probability x equal to hat given y equal to hat. So actually, while you guys are computing or something, maybe I can I can try to kind of like estimate it with my experiments here. I already like did a 10,000 experiment here. I can use this use this experimental results here, simulation results to estimate this probability. So how many of this is y I had? Let's see. This I can just use space rule, right? So this will be like I want to see like how many of these are both x and y had. So x, let's see, equal to 1. Maybe okay, maybe I can do like this. I know it's a little bit weird. This x equal to 1 and y equal to 1. This actually pull out like all the x values that x equal to 1 and y equal to 1. Okay. And if I count total of them, so that's like 7,000 of that, or something like that, close to. Let's see if I just look at how many of this is like y equal to 1. Say 70, 64. So I guess if I do it correctly, the probability will be approximately, maybe I just write more for it. Let's see. Okay, it's a little funky, but this does the job, I guess. It's a little bit high. I don't know. But I got some kind of estimate like this. X, Y. Maybe I can try to do a more experiment to see like if I get result. See if I want to do. Remove this. Use 10,000. Let's see. Does it take long? Okay, it doesn't take long. So let's see. 0.95. It's bigger than I thought. Yeah. Also, like I let's see if like I did any mistake here. So let's see. Let's just make sure that things are correct. So probability that y is hat. Both. Let's see. Okay. Let's do it. So this one. Probability for this is like equal to joint probability, right? I can x equal to hat, y equal to hat over p, y equal to hat, right? So this is just space rule here. So what's the probability I can x and hat and y hat? So think of like I have w like starting with always hat. So x is hat, then it will be like this pathway. It's I got hat here, that's a x, y, and then y hat, I got h here, right? So the probability for that is like 5, 6, and 5, 6. So the probability to be like both x hat and y hat should be 25 over 36, something like. Now probability y equal to hat. Yeah, I think like probably I made mistake maybe. So or maybe right. So probability y equal to hat. What's the probability of y equal to hat? So I can have like this situation, like this one, I get y equal to hat, but also have this one will get y equal to hat, right? So therefore probability y equal to hat will be equal to like 5, 6 times 5, 6 plus 1, 6 times 1, 6, right? So therefore it's equal to, okay, this may not be too bad. Maybe the estimate is correct. So it's like, let me try to compute that. Okay, actually I can compute here, right? So if P2 equal to 5 times power 6 times 5 over 6 over back 5 over 6 times 5 over 6 plus 6 times over 6. So okay, it's exactly. So it's like 0.96, like something, 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 something. So our estimate is quite close, like it's reasonably close. So again, you see like even like this kind of probabilistic approach didn't give you, or no, I shouldn't say probabilistic approach. I mean, this Monte Carlo approach or like probabilistic programming approach doesn't get you the exact value. If you have a chance to really what should I say, have time, like have the you can indulge yourself like to do a little bit like verification like this, like just a couple lines of code. You can really prove your result much better because it's easy to make mistake like for this kind of probability problem, right? As you see. But I honestly, when I first see the result, I'm not certain as well. Like, okay, is that like some bug out there? That's not px equal to h. It's px e. Okay, this one here. Let me just write here. Is equal to base rule will be h y equal to h over probability x y equal to h. So probability x equal to h is not 1/6 over 1/6. Yeah, it's 1/6. 1/6 is probability. Actually, the one you just wrote is like the probability x equal to tail and y is equal to h. There will be 1/6 times 1/6. Yeah. So again, like the denominator here, we are using marginalization, right? We are this denominator here on the paper. No, I y equal to h is not here, right? So this is like x equal to h and y equal to h over like py equal to h, right? Okay, I cannot see your chat here. No, 1/6 over 1/6, this is two terms and this is using marginalization. This one is equal to what? It's equal to py equal to h plus x equal to h. Oh, sorry, py equal to h, x equal to h plus py equal to h, x equal to tail. And this one is equal to 5/6 square. And this one is a 1/6 over 1/6 square. Yeah. So, okay, I guess that's it. Yeah, I guess I'm also like with that simulation, of course, you can ask like many other questions. For example, like you can ask, what is x equal to hat given z equal to hat, let's say. So I can ask this also like, this value is not, no, okay, this is confusing. This value is not the value that's supposed to be the outcome. So I can ask something like that, like x equal to hat, z equal to hat. Then to do that, like I should have like x equal to hat and just change this to c equal to hat, right? And this is a c equal to hat. Let's say this is a x equal to hat and c equal to hat, let's say. Then I can get that probability. And you can ask all kinds of like similar probabilities as well. Just simply using base rule and do the counting. Once you have did enough experiments. And if you're trying to like compete the extra credit for your homework, you're basically using something similar to that. There's some questions I believe to ask you conditional probability. Then you can also use base rule to expand that. Once you expand that, like you have this cup joint probability you can find. It's just like what's the probability, or just count all those experiment that satisfy all the conditions that will compute the joint probabilities. And also like for the probability, it's the same thing. So it's just you reduce the number of condition there. So okay, I guess that's more or less I like to talk about for this probabilistic programming for this moment. Now I want to the next thing I like to do is I want to do a kind of introduction for influence with, let's see, let me just pull out my slide here along the way, then say, sorry, I cannot see your chat. I need to pull back the chat. So next thing I like to talk about like maximum likelihood. I guess some of you probably learned it from other classes. Maybe okay, like it's like a question or poll, like this kind of thing. Like, did you learn like map maximum likelihood? Yeah, I probably have a spelling mistake here. Likelihood estimation. So did you heard of that like in some other classes? This is a MAP is a maximum a posteriori. I don't know. Is it? Yeah. Probability or something like that. Good. Yeah. So I guess this will be more or less a review as well. And do you know the difference with like Bayesian inference? Like this Bayesian inference. So actually map is very similar to Bayesian inference. Like sometimes people will get confused with them. So okay, I guess I see many of you actually know that. So it will be like a review, but hopefully it's not too bad. So I will go like reasonably quick then. So I will take an example here. Sorry, I borrowed this example from a class from University of Washington. So it's basically you have three different cons here. So I have like con 1 that have like probability of hat over C1 is equal to 0.1. I have con 2 here. This con 1 is con 2 here. Probability hat given C2 is equal to 0.5. So this is a fair con when it's unbiased. So one of the con is like both two con is kind of like is loaded. Do you call it loaded or like this con is like unbiased? It's biased. Con 3 will have the probability of head is higher than probability of tail. Like it's much more biased to head. So I have like three different cons. They are not distinguishable. Let's say, and you're basically like you have a bag again. Like you have a bag. Well, dry. I don't know. I'm very bad drawer, bad artist here. So maybe I have a bag here. So I have some cons here. There's some of them is con 1, some of them are con 2, some of them are con 3. So to start with, let's say assume I don't know how many cons are in the back here, and then they are all in the back. Now I'm going to kind of like draw one con from the back here, and then I'm going to flow it for it maybe multiple times. So based on the outcome, I try to estimate which con I have. So from the setup here, apparently, if I fold the con, I pick a con here, I fold it like 10 times, I got 10 hat here, then it's very likely that I'm kind of like getting this con, right, the con 3, right? Because con 3 is biased to have a very high probability of getting a hat. And if I got like all tails, then most likely I got con 1 here. So the question is like, how do I estimate which con I actually pick. So so if I don't know, so now I mean like the difference between like maximum likelihood from map and Bayesian inference is that like for this case we assume we have no pi information, no pi. So if I don't have any pi information, like the best guess would be like, I'll just assume that like the back have uniformly, I mean the same number of like con1 and con2 and con3. So it's good to estimate that like the pi probability of C1 is equal to probability of C2 is equal to PC3 is equal to 1/3. So this is like probably the best thing I can do. And let's say if I do some experiment here, and I let's say if I got maybe just do one I picked I after I picked the coin I just fold the coin once, and let's say I got a head. I got a head here. First time I got a head. Then let's say if I want to compute what's the probability of CI given head. So this one will be equal to oh wait, actually maybe I will leave you as a exercise here. PC1 given head is what? Well, you guys are quick. Well, PC1 given head is what? So assuming that like I have no information here, I have PC1, PC2, PC3 is equal to 1/3. P hat, so I have the P hat given C1 is equal to this, P hat equal C2 equal to 0.5, P hat given C3 equal to 0.9 here. So what was PC1 given hat? So I just picked that con once, and I got a hat. Now I ask like what's the probability that con is actually it's actually con one or like type one con. Yeah. So um, okay. Hmm. Okay, I guess I will just give a couple more steps just as a hint. Of course, we can just use space rule here, right? So this is PC1 H over PH, right? Now then this probably is easy to compute. So this I can do base rule again, like this would be like PC1 times PH given C1 here. Now, how do I compute this guy here? So this is we're going to always kind of like, you see like actually you see like this kind of like honestly this kind of probability problem is quite easy after you get used to that, because it's always more or less the same as I basically the as I mentioned at the beginning, this like dummy approach of solving probability problem, like you just like insert some random variable, um or like if you don't know what's pH, then like see like how are we able to kind of like, I mean, like insert some kind of variable, like and marginalize that, and those individual terms I'm able to compute that. Like I don't know how to compute pH directly, but I know each of this PCH, right? So this one will be equal to PC1H plus PC2H and PC3H, right? So it's just doing marginalization again. We have three different C's here, conv1, conv2, and conv3. And then each of these, I can just use space rule. This would be like PC1, PH given C1, this PC2, PH given C2, and PC3, PH given C3. So if I assume that all cons are uniformly chosen, then would be like 1/3. I have all this 1/3 gone cancel. I can forget about it. So in the numerator, I will just have pH given C1 that's equal to 0.1 here. Denominator, I have like 0.1, I guess like 0.5 and 0.9, I believe. Is that, yeah, something like that. So this is actually, I think it's 1/15. Yeah, actually, I think I reached is correct. So, so this is PC. And then I can also similarly, like I can compute like PC2 given H will be some value. Actually, what do you expect? Like PC2 given H should be bigger or smaller than PC1 given H? Is PC2 given H bigger or smaller than PC1 given H? But yeah, the question is like, okay, okay, I guess like this question may be too simple after you know how to compare PC1. But just a quick question, like, so of course you, yeah, maybe I see the question. Maybe, okay, I'm not going to ask this because PC2 given H, of course, is like just 0.5. You see that it's like just 0.5 or 0.1 plus 0.5 plus 0.9 here will be bigger than PC2 give PC1 given H here. But also, like, you can just look at the problem itself, like without doing any computation. Just think of like what is the problem precisely representing. Uh, what is the probability if you get ahead, what is the probability that that con is actually C1, and what's the probability that the con is actually C2? Of course, it's more likely like the con is C2 because like C2 is more biased to be hat, right? So if my first experiment outcome is a hat, then just like kind of like based on intuitive arguing uh, from the setup, it's more likely that the con is C2. And then like and I can also compute C3 is actually C3 will be even more likely, right? Because I mean PC3 given H, that would be like 0.9 over 0.1 plus 0.5 plus 0.9 will be even bigger. So therefore, like the final conclusion is that like I will have like PC3 given H is biggest, right? So based on like maximum likelihood, I will argue that okay, the con is likely to be C3, something like. the coin that I actually picked from the back, and I fold that coin to get outcome H is likely to be like coin 3. So now let's change that a little bit, like not change, but like append uh, some more information to the current setup. Let's say if I did the experiment, like not just one time, after I pull the coin from the back, I fold the coin twice, and I got like a head and a tail. So first time I got a head, the second time I got a tail. Now I can recompute that, right? So based on like my experiment, again, I want to ask question like, what is the probability of CI given head and tail? So if I ask you like, what is the coin that actually pull from the back? The coin should be just estimated as the coin that maximize this probability, right? That more precisely should be arc mass probability CI given HT, right? So this will be the coin, right? The I hat will be the index of the coin, right? So again, we should compute this conditional probability, but now with both head and tail here, I don't know, maybe I just, let's see. Let you could compare one of them again. Maybe just PC2 given HT here. What's the value for that? I guess you need a little bit computation, just like the previous case. Yes, PC2 given HM head and tail. Yes. Mm. Oh, wait. Oh, yeah. No, why 99% actually? Uh, the Oh yeah, but yeah, actually the it won't. It's not really that big as you thought. Yeah. Um, Maybe if you have like 100 head and 100 heads and 100 tails, it will be very close to 99 something. But this is like just one head and one tail. It's actually not that extreme. Yeah. Uh, okay. I see you guys maybe just giving a guess, or like this is like the value you try to you evaluate. You again, you space rule, like we are engineer, or like at least like I consider myself engineer. Just like you engineer doesn't use a brain, to be honest. Like I just do like something like cast what I say? Like um I before I do anything like intuitive, of course sometimes you need to use intuition, but sometimes just need to just uh repeat the steps that I learned in the past, and then like that um doesn't need to think that much. Yeah. So here, like again, like using base rule, right? So I should start with base rule here, right? PC2, head and tail, right? Maybe I just omit those comma here. So the head tail over like P head tail, right? So look at the numerator. What is that? That is, it will be P. I can expand it the other way. I don't know. I don't know how to compute this. But I know to compute like the John probability the other way. I know like PC2 and then PHT given C2, right? So, and over PHT here, I say PHT here. So this one, of course, I know is 1/3 if I assume the probability is uniform here. For this guy here, this is actually using the conditional independent assumption. Intuitively using this, but it's also like very natural because I picked the con like the if you know that like which con you're picking, the first time, or like if once you fix the con, like maybe I don't even need to know like which con I picked, but once you fix the con, the first time you fold the con, the first time, and then the out the result for that, and you fold the con second time, the result for that, the two events to be independent, right? So what I mean is like this should be just equal to like P H given C1, C2, sorry. This just this value here is PH given C2 times PH given C1. Right? And PH given C2, oh sorry, I'm sorry, PH is given C2 and P tail given C2. I need to be careful. PH given C2 and P tail given C2, right? PH given C2 is what? Is 0.5. And P tail given C2. I know P hat given C2 is like 0.5, then P tail given C2 is just 1 minus 0.5, right? So again, it's like 0.5 here. So therefore, like the numerator is like 1/3, 0.5, 0.5, right? Now the denominator, I don't know how to compute it directly, but again, I know that like P hat tail is equal to P hat tail C1 plus P hat tail C2 plus P hat tail C3. Again, I'm just using marginalization, right? I have like C as a dummy variable here. I sum exhaustively for all the cases. So I put in the variables, but then sum all possible outcomes, then that variables will be eliminated eventually. So I get back this. So therefore this sum will be just equal PHT. And for each of this value, I can compute just as the numerator, right? So precisely this one is just the same as numerator. So therefore it's like just 1/3, 0.5, 0.5. And the other one is like, this is be 1/3, I have like pH given C1 times P tail given C1 would be like something like 0.1, 0.9 here. And this would be also similar let me see, maybe 1/3. This is 1 here times 0.9 times 0.1, something like this, right? So therefore the value should be, if I just copy from the notes, should be from 5.8. And if you're trying to compute the other values like PC1 given HT should be equal to 0.21, and PC3 given HT is also equal to 0.21. So therefore, it's more likely to be the second con, as I was, which is a intuition is correct, but it's not that extreme. Also, like it's just less than 0.6 probability. Say yes, less than 0.6. Yes, less than 0.6 probability that is actually C2. Now this is a maximum likelihood estimate without using the pi information. Now if I give you some pi information, let's say if I know this con, like I know how many type 1 con and how many type 2 cons and how many type 3 cons. For example, like if I tell you that like maybe there's actually 100 cons in the back, and all of that like 5 cons, like C1 have five con, type 2 cons have like 25 cons, let's say, and type 3 cons have 70 cons, then my estimate can be completely different, right? So in this case, actually the computation for both map and maximum likelihood is essentially the same. But for example, if I have the same question asked here, what's the probability that I have a con, which con, like for example, was C2 given head and tail. Now I need to adjust with my prior knowledge now. So now I know that like PC1, PC2, and PC3 are not the same, are not equal to 1/3. But PC1 will be like 5/100, will be like 0.05 here. PC2 will be like 0.25, and PC3 will be 0.7 here. So therefore, like if I modify that, let's see if maybe I change another color here. If I modify that, then PC2 here will be like this multiplied by 0.25. This is multiplied by 0.05. This is 0.25. And this is a 0.7, let's say. Then actually the value you will get, let's see, will be 0.481 here. And PC1 given head and tail will be equal to 0.035. And PC3 given head and tail will be like 0.485. So in this case, given this pi here, you actually, given that like I have like head and tail, I will guess that like the con is still like based on my calculation. I will still believe that the con most likely to be like con 3 instead of like con 2. So because I know there's so many more con 3 than con 2 here. Yeah, same here. Actually, I'm lacking coffee. I'm also I had my coffee, but I had lack of sleep. I slept like 5 hours yesterday. It's so bad. Like for a week already, it's like crazy. So anyway, yeah, I'm not that kind. I need like 8 hours sleep usually, but recently I just didn't have enough sleep. So let's see. Uh, okay, you guys are kind of clear for that. Like, I hope like it's quite clear for like maximum likelihood and map. You see, like the difference here is just I have pi, I'm no pi, and I assume that you guys won't have too much problem uh, understanding this difference because I guess it's more or less a review for you. because you mentioned you saw this before in other classes. Uh, Now for Bayesian inference, uh, I cannot actually use this ask this question like, to illustrate what's the difference of map and Bayesian inference. But instead, like let me ask a different question here, a slightly different question. Uh, what is, let's say here, I have as this, okay, I guess I can just use the same setup here. So I kind of select a coin from the, I guess I draw a coin from, I drew a coin from the back, and then I fold it twice, I got a head and tail. Now the question, rather than ask you to kind of guess like which coin I pick from the back, I'm going to ask you like, if I fold this coin again, the third time, how likely I will get a head? Given your observation that the previous observation is head and tail. So therefore the question will be like, um, maybe I say the outcome of the draw is a, or maybe I simply write like this: what's the probability of head given head and tail? So okay, hopefully you are not confused with this notation here. This is an observation like first time you got a head, second time you got a tail. Like what's the probability that for me to fold next got a head? Now, if I'm doing a, let's see, a maximum likelihood or map estimation, what I'm going to do is I first estimate which con, kind of guess at which con I actually pick from the back. So for this setup, as I already showed, if I'm not using any prior, originally I will, if I use maximum likelihood, I would guess that like the con I pick is the second one, right? Because like that one have the highest probability to get head and tail. So therefore, like probability to get a head for the third time will be just equal to 0.5 maximum likelihood. That's maximum likelihood case here. I hope you're following me. Let me just ask you here now. So for map, what will be the probability for that? This is a third time. This is a first and second time. Again, I'm assuming using this prior here. What will be the probability to get a head, given that like the first and second time I got head and tail? So is my question clear? Yes. Using That's I don't know. I don't know actually. Not. I didn't compute it yet. Maybe I should like. I assume like that the number should be correct from the notes, but maybe I should. Let's see. Let's see. Um. Okay. I guess I maybe uh. Yeah. Actually, these questions. Yeah. I probably it's my fault. Like. This question should be simple. I guess I probably like go too fast about the explanation of map and maximum likelihood here. So maybe I draw one more step here. So if I'm trying to estimate, how do I do map estimate here? Let me see if I can find some space here. Maybe like I just use space here. So if I try to do that, if I do a map, so what I'm going to do, I basically I'm trying to find a optimum estimate CI is equal to, maybe, yeah, maybe I just write CI will be the arc mass, or like maybe I had the probability of CI given head and tail, given the observation of that, and then the estimate of PH given head and tail will be simply estimated as, maybe, how do I then, maybe I put like this, estimated as P hat given CI hat here. Here, actually, like map, both ML and map is essentially doing the same thing. Just like when you compute map and ML, the difference is like how do you compute this, or like do you incorporate the pi probability in computing this conditional probability here? So for ML, like if we have head and tail, we know that like the one that the most likely con is C2, right? Because like PC2 given head and tail is like 0.5 something, I guess I forgot. And the rest is like 0.21. I guess this is 0.58, the other is 0.21. So this one is largest, therefore like the con that I guess that I actually pick is I just con 2. So therefore like the probability of hat given this head and tail will be just approximate as a probability hat given C1. That's okay. You don't use this information anymore, but the cons that's 100 back, 100 cons in the back is a prior, right? So it determined like how many, what was how this PC1, PC2, and PC3 is supposed to be, right? And because I mentioned earlier, I have like 5 cons here, 25 cons here, 70 con here. So therefore, like this PC1 is actually 0.05 here, PC2 is a 0.25, PC3 is 0.7 here. Yeah, actually, we should have the comment. I'm not quite sure. You mean ceiling? You mean the maximum? Is that right? Oh yeah, I guess I got just pull back this question here because all of you like um not exactly. I guess let's just forget about the question. Let me just like answer it myself. Um, for the maximum likelihood, so maybe I just write precisely for maximum likelihood. Let's do ML again. Let's do ML again. We compute like PC1 given HT is actually equal to 0.21, right? And PC2 given HT is 0.58, right? PC3 given HT is equal to 0.21. So therefore, like based on the observation head and tail here, C2 is most likely to be the con, right? So therefore, like I would basically pick like con2 is as my guess. I would think like, okay, this is my con2. The con I pick is actually con2. Therefore, like probability of hat, the next time I'll get a hat is actually, given this observation, it's just like PC2 given hat. Sorry, for what I'm writing. PH given C2, right? So this is a ML. And so therefore this is, I know what's pH given C2 is simply 0.5, right? So therefore this will be from 5, right? Max here is like maximizing across different possible cons here. So yeah. So and so is that clear for maximum likelihood now? So map is essentially the same here, right? It's actually precisely the same. Just you will get a different estimate, right? Because a different estimate of the conditional probability. Because now your PC1, PC2, and PC3 is no longer uniform. You get different values for that. I think like the values we got there is something like, let me see if I can pull it out here again. It's like 0.035, 0.841, 0.845, something like that. So because in this case, we have the prior, knowing that there are many more like con3 than like the other cons. So therefore, like it's kind of skew the distribution, right? So therefore, like even though like I got the observation is head and tail, actually it's still more likely to be con3 here. Now, therefore, if I estimate like what's p hat given head and tail here, it will be like using map will be like p hat given con3 here. So it'll be equal to what? If I have the conflict is heavily biased to be head, right? I remember that, or tail. I forgot. Let's see, tail or head. Head, yeah. So therefore, it's like 0.9, right? So is that clear now? For maximum likelihood and map. So you see, like both of them is quite. You see, like this has some problem, like using this kind of estimate, because you see, like for map here, if I adjust this value a little bit, like I can get C2 maybe like it's better than C3. Maybe I just can scale down this 0.7 to a little bit to 0.65 something. Then I will have like this. Okay, yeah. So, but let me know like if you have any immediate question here. Okay, okay, yeah, yeah. So okay, I guess I'll just briefly mention like the Bayesian approach, and then we just end here. I guess like, everyone is tired probably. So, but I just want to give you the intuition here, like why this has a problem, like for map and maximum likelihood. So it's a very reasonable way to do things, right? So basically, I say I have some. In general, there's some other problems. I say I have some hidden parameters. Like, let's say some filter here. Now I have some observation O here. Now O1, O2, O3, and so on. And maybe I just write O1 and O2 have two observation, or O2 and O1 up to O9, let's say. Now I want to predict the next observation, O10 here. Now if I'm going to use a map our maximum likelihood, what I'm going to do, like I estimate the model first. So the model parameter off screen, so you cannot see my writing. Let's see. I think I can see my writing on my let's see. Maybe it's like let me use and let me write here will be better here. Theta. Is that okay? Can you see it here? O1, O9. Okay. Yeah. So let's say like in general, let's say I have like this is like not just a this is a toy problem, right? But this setup is very common. Let's say I have a model here. It's like kind of like explained by this model parameter theta here. And I have like a number of observations. Maybe I have 9 observations here. Now I want to predict the next observation O10 here. I have several ways to do that. Like I can do this map or maximum likelihood approach. Basically, it's like based on my previous observation, I'll first estimate what is my theta here. So maybe like my best theta head, of course, is the one that's going to maximize the conditional probability theta given the observation here. So this will be my optimum filter, optimum parameter, optimum theta here. Now then, given my optimum theta, I'll simply estimate, let's say, what's the probability to have this particular observation, O1 or O10, given the observation O1 to O9 as a probability O10, given this theta hat here. This is basically ML or map. Now for Bayesian, you see like the problem is like I can be pretty I would say uh um too too extreme in the sense I just pick one model out of many models, pick the peak model. So for Bayesian, I will kind of like do a weighted sum for the estimation instead of like just pick one optimal model and use that for estimate. So instead, like if I do a Bayesian estimate, I'll just do a weighted sum. P010 given like 01 up to 09. So what I'm going to do, I'm just like estimate this as a P010 given theta, P theta given 01, 09, and sum over theta. So what you see is that like I'm basically I will consider all the possible model here, right? But I'm going to weight the sum like this model, this estimate. I mean, I will consider all the theta, all the model here, and compute the estimate. What's the probability of the next observation given that particular model. But I'm going to weight the sum this estimate by the probability that like that model actually occur given the observation. The nice thing about the Bayesian estimate is like this is actually like the reasonable way to do things, right? Because if you look at that, this is not approximation, this is exact because this is Bayes rule, right? I'm writing here is like what I did here is just I'm writing actually, or like this is equal to, let me write it another way here, is equal to P theta O10 theta, sorry for my handwriting, O1 up to O9. So this thing is always true because of marginalization, right? So I insert theta and I marginalize that. So this is always true, right? Now I'm going to use Bayes rule here. Theta, theta given O1, O9 times P O10, sorry, O10 given theta O1, O9. So you see, I'm almost the same as here. The only assumption I made is like the conditional independence. So I'm assuming the model parameter capture everything. So as long as I have model parameter, the rest is not important. So okay, like times is up anyway. So I guess I will just stop here. So maybe I will come back and review a little bit the basic what we just mentioned here. And then I will start a new topic. So I'll see you guys next week. Yeah. So by the way, if you guys have any questions, I'm happy to stay. But like you can send any questions to Discord as well. Yeah. Okay. Bye now.